All right, let's dive into the invisible world of electric charges and fields. Seriously, this is the stuff that powers pretty much everything, from your phone to the atoms in your body. It's even behind that little static shock you get from a doorknob. So let's get into it.
You know that feeling, right? You shuffle your feet across a rug, you reach for something metal, and zap, you get a tiny little shock. Or maybe you've seen a balloon make your hair stand on end. We've all been there. But what is actually going on in that little spark? It seems like magic, but I promise you, it is pure physics.
That spark, and honestly almost every electrical thing you can think of, all comes down to one single fundamental property that the tiny particles making up our world possess. You can think of it as the main character in our story today.
And here it is, electric charge. You really can't understand electricity without first getting a handle on charge. It is the absolute starting point for everything else. So, what is it?
Okay, think of it like this. You know how things have mass, and that mass makes them feel the force of gravity? Well, charge is kind of like that, but for the electromagnetic force. It's just a built-in core feature of particles like electrons and protons. It's not something they have, it's part of what they are.
So charge plays by three very strict, very important rules. First, it's additive. You literally just add the pluses and minuses together to get the total. Second, it's conserved. You can't just make charge appear out of nowhere, and you can't destroy it. You can only move it from one object to another. And third, it's quantized. This just means it comes in tiny, indivisible packets. You can have 1 electron's worth of charge or 2, but you can never, ever have half.
Now, how easily this charge moves around totally depends on the material. In things we call conductors, like a copper wire, those charges can just zip around freely. It's like a superhighway for electricity. But in insulators, like the rubber coating on that same wire, the charges are basically locked in place. They can't go anywhere. And that simple difference, right there, is the foundation for pretty much all modern electronics.
Okay, so we've got this property, charge, and we know it creates forces. Well, it turns out there are some really simple and honestly beautiful rules that tell us exactly how these charges push and pull on each other.
It's all wrapped up in what's called Coulomb's law, but the idea is super simple. If you have 2 positive charges or 2 negative charges, they're going to push each other away. But if you have a positive and a negative, they're going to pull toward each other. The basic rule, opposites attract and likes repel. And just like with magnets, that force gets way, way stronger the closer you bring them together.
But wait a minute. This leads to a really strange question. How does a charge way over here even know that another charge is way over there, telling it to move? I mean, there's nothing between them. It's just empty space. This idea really puzzled scientists for a long time.
It's a real head-scratcher, isn't it? There are no ropes connecting them, no secret messengers running back and forth. How is this force being communicated across a distance? Well, the answer is one of the coolest and most powerful ideas in all of physics.
And the answer is the electric field. See, a charge doesn't actually pull on another charge far away. Instead, what it does is it changes the very fabric of space all around it. It creates this invisible field of influence. A great way to picture it is like putting a bowling ball on a trampoline. It creates a dip, and any other ball that rolls nearby is going to feel that dip. That's the electric field. Any other charge that wanders into this field feels a force right at that spot.
Now, to help us see this invisible field, we draw something called electric field lines. Think of them as a map. The lines show you the exact path a tiny positive charge would take. They always point away from positive charges and towards negative ones. And here's the key. Where the lines are packed tightly together, the field is really strong. Where they're spread out, it's weak. Oh, and one very important rule. These lines can never, ever cross.
A perfect example of this in action is the electric dipole. Now, that's a fancy name, but it's just a positive charge and a negative charge sitting a short distance from each other. And you see this pattern everywhere in nature, like in a simple water molecule. Understanding the field from this simple little pair is a huge step toward understanding how all sorts of molecules interact.
Now, as you can imagine, trying to calculate the electric field for really complicated setups with tons of charges can get incredibly messy. But physicists have this amazing, elegant shortcut they can use. It's called Gauss's law.
Let's not worry about the heavy math here. Let's just get the big idea. Gauss's law basically says this. If you imagine drawing a closed bubble around a bunch of charges, the total amount of electric field poking out of that bubble depends only on the total amount of charge you trapped inside. It's a fantastic shortcut. If you know what's inside the bubble, you can easily figure out the field on the surface.
And this is not just some neat theoretical trick. For situations that have a lot of symmetry, like a long straight wire, a huge flat sheet, or a perfect sphere, Gauss's law turns a ridiculously hard problem into something surprisingly simple. It really is a master key for cracking these kinds of problems.
So there you have it. We started with something as simple as a static shock and ended up talking about the fundamental rules of charge, the forces between them, these amazing invisible fields, and even a powerful shortcut for understanding it all. Every one of these ideas is the absolute foundation for how we understand our electrical world.
We've just explored this invisible architecture, the electric field, that organizes so much of our universe. It kind of makes you wonder, doesn't it? As you go about the rest of your day, what other invisible forces, what other unseen rules are quietly shaping everything around you? Now that's something to think about.